Well, good morning, everybody. We're going to look at Ohm's Law today, 6.2, and we're going to start off with just talking about a few definitions. Some of them you may be already familiar with. So resistance is simply the pushback or an impediment to smooth flow of electrons. And we put dot 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 of electrons in this case. Okay. A resistor is a piece of a component of circuitry specifically designed to give a certain amount of pushback. One of the really, we talk about current, for example, and it's actually a really good word to use because if you can imagine, a pipe, and in fact, sometimes it's helpful to think of wires and circuitry as a series of pipes and whatnot. If you have a clean pipe, water flow is going to be unimpeded, and you won't see any drag. Well, hardly any. But if there was, say, deposits or narrowings in the pipe, what you would expect to happen is that the flow would be impeded with, or the actual flow would go down, and that is actually true. But and the more narrowings, if there are more resistance that you put in it, the greater the overall resistance. So if you were to think about this as a wire, and you had, say, I'm going to try to draw this. Here we have a do it all along here, and this is the negative end. So electrons are going to flow this way, right? Okay. And if I was to say to put in a resistor here, and another resistor here, another resistor here. Now for you and I, when I do this, I like to just put in what the values of the resistance is in here. So for example, let's say this is a single cell battery, and so that means that the what do you call this, the voltage is typically 1.5 volts. Well, let's say that this resistor was specifically designed to give 0.1 ohm. Ohm is the unit of resistance. So maybe what I should do is, this is measured in ohms, and typically we use the symbol omega. And let's say that these weren't in place at first. Let's just say that we have this wire. I've left room for these to be resistors. So let's suppose that you only have one resistor in place. Well, if you have that, the current is going to be greater than if you added another identical resistor and a third identical resistor, right? So we'll look at Ohm's law in a minute, but intuitively you should equate this with this. As these resistors in the same wire in series are added, the resistance goes up, and so the current, the flow, goes down. Okay, does that make sense? Nobody, I don't hear you. Sorry, can't hear you. Why did I ask that question? I don't know. I just asked it. Superconductor, as the name implies, is a special metal at low temperatures which produces virtually no resistance. Okay? And the last thing is that power, this is a measure which is the product of the electric potential which is volts times the current. And that is measured in amps. Okay? So Ohm's law, this is Ohm's law here. This is Ohm's law. That's an H. Ohm's law. V equals IR. And the magic triangle, I would include this on your cheat sheet. V is equal to I times R, and we're going to solve different things for this. So let's just use this right now to determine what is, in this situation here, what would be the current in this situation. I want you to solve for that right now. Pause it, pause this video, solve for it, and then come back. Okay, how you should have solved for this is that you're looking for I, you're looking for current, and that is equal to V over R, where voltage is 0.1 no, I'm sorry, start again, 1.5 volts divided by the sum of these, which is 0.3 ohms. And so that obviously is going to be equal to 5 amps. Okay? Good. Okay. Let's take a quick look at the next page here. Resistors are typically really, really small, and to try to write on them and be able to read them is well nigh impossible. So the electricians have come up with this handy code where they use colored bands in order to what would you call it, to determine what the actual working resistance of any what do you call it, resistor might be. So imagine, if you will, that we have a suppose this is a sample resistor. Now it's going to be really small. These are really, really small, but I made it larger so that we could color band it. And let's say it typically has 4 bands. And let's say, no, that's too fat. Let's say the first one is green. Okay. And the second one is orange. And the third one is blue. And the fourth one is silver. How am I going to do silver? Okay, you're going to have to trust me on this. You know what? I'll outline it in black so you can actually see it. And I'll use pencil, because that's kind of like close to silver. Okay? So this is the first digit. This number here, this color here, represents the first digit in the resistance. The orange one, this represents the second digit. This blue is called the multiplier. Okay, and this one here is the tolerance. And tolerance is basically a plus or minus %. Okay, so try right now, try to figure out from the key that you see here in this table what the actual resistance is, and then come back. Okay, you're back. Okay, so green is 5, orange is 3, the multiplier is 10 to the 6th, and the tolerance, silver, is plus or minus 10%. So this, if we had a resistor like this would be 53 1, 2, 3, 4, 5, 6 ohms, plus or minus 10%. Pretty straightforward, eh? Maybe try another one on your own, and maybe you know what you can do? Try reversing these colors. Try to make one, draw it under here, where you've got blue is the first, orange is the second, green is the third, and make up a new tolerance, and then solve for it. Okay? Okay, let's see now. We'll do some sample problems in another video. I'm not going to do it all in one. I'm going to break this up today. So there are two, actually, down the bottom here. This has got like a super handy wheel, and I'm not sure how exactly you'd want to incorporate this. You can use the triangle, but this is actually a more comprehensive. I don't know. You can maybe Google image this, and if you have a printer, you can print it out and paste it onto your cheat sheet. I'd be okay with that. Okay, but inside here you can see that from just the V equals IR that we are simple Ohm's law. You can see that Ohm's law is buried in here. You see that resistance here is equal to V over I. You see that I is equal to V over R. Voltage is I over R, or I times R. So you see at these three corners, this is just the Ohm's law. Joules' law. So this is all what I would think of as this is ohms. Joules' law is here, and instead of memorizing all these, if you incorporate those, you'll find that that these will solve for what you see there. Plus, because current is in both of current and resistance live in Ohm's law, but they also live in Joules' law. Here's resistance, and there's current, and there's current. Then these other ones, these other non-yellow ones, are reflected in this wheel as well. So instead of trying to memorize that, because a lot of the electrical is going to be just plug and play, then that would be it. You'd have everything, Joules and Ohm's law, handy. Okay. Now, last thing we want to do is I've incorporated this into your talking about terminal voltage. Terminal voltage means like how much voltage is at the terminals of a battery, for example. Now, batteries are typically rated at like dry cells are like 1.5 volts, but there is a certain amount of resistance that's inside the battery itself that actually lowers it. Now, it's not going to lower it by a lot, but it's going to lower it by a bit. So this is the equation for terminal velocity. Terminal velocity. Oh, I just crack myself up sometimes. Terminal voltage is equal to the E, which is the electromotive force, which is basically another measure of voltage, plus or minus the current. That small r is internal resistance. Okay? So let's label these things. So this is internal resistance. this is current. This is basically this is EMF, electromotive force, or basically the voltage produced by the dry cell. And in this case, this is going to be 1.50. Oh, it's here. So what this diagram here is this thing here, this dotted line, so represents a dry cell battery. Okay, so you have a total voltage here, which is the 1.5. So that's this. This is the 1.50. You have an internal resistance, which is here. This is the resistance within the battery. That's orange, by the way. Okay. And what they're saying is they're adding a second resistor, which is here. Now this, I apologize, excuse me, because I imported this diagram. This should be not small r. This should be capital R. This is a resistor. Okay, so can you see that? Okay, so this resistor here, the blue one, is given as 2.0 2.0 ohms, and the internal resistance is given as this. Okay. Now, in order to figure out what the voltage is of the whole thing, you have to start with this and eliminate this, subtract that, and that's the whole idea. Okay. So the first thing you want to do is because going back to Ohm's law, current is equal to voltage divided by resistance. So the current, we have to find the current first. So this is job one. This, I know this is not, doesn't show up very well, but this is the current. Current is equal to the voltage, the overall voltage, which is the electromotive force, okay, divided by the sum of these two resistances. Okay, so this is resistance 2.00 plus 0.050. That should be a dot there. This gives us an overall current of 0.732 amps. Okay, so this is current. Okay, now this is what we're going to substitute into here to find the terminal voltage. So terminal voltage, I'm sorry, so the voltage, this sub A, that's a B, hard to see, sub AB. This is the voltage. If I put a voltmeter across here so that I touched one end of the battery to the other end of the battery, and I got a reading. So that's what that's talking about. So the terminal voltage is equal to the electromotive force, which is 1.50, minus the overall current times the internal resistance. And when I calculate that out, it comes out to 1.46, which is that's a little bit of a voltage drop for the entire battery, and that's pretty much it. Okay, so we've been going for 24 minutes now. I'm going to take a break. You should take a break, and then when we come back in the next video, we'll do a couple of examples and then call it a day. Okay.